point because we'll get to them when we get to them. Right, so this talks about optimization strategies. Let's first talk about why I think about this so much. As I mentioned, I'm part of a work-for-hire team, and we've been working on console support for a game called King of Meat, which is a game made by Glowmate and Amazon Games, and is out now. Now, we've been part of this for the past 3 or so years, with 6 to 10 programmers, depending on sort of the phase of the project. And of that group, there are 3 graphics programmers, including me. Now, the graphics group primarily focuses on porting the graphics engine to various consoles, and then optimizing the rendering workload to make sure it actually runs. Now, we do also sometimes implement new features, etc., but it's not really important for this talk. Right, so optimization workload is inherently undefined. When I joined this project, I knew that there were some platforms that weren't performing well, but I had no clue where the bottlenecks were. And even if I did know them, bottlenecks are constantly changing. The game was still in active development, and optimizations can often unveil unknown or previously hidden bottlenecks, or render previously notable bottlenecks irrelevant. So we had around 2 to 3 years to fill with an empty backlog. We needed some form of strategy. Right, so that's not supposed to happen. Before we talk about our approach, let's talk about how you find things to optimize. Basically, where the optimization come from, what's their origin. Now, the first source is ideas. As a programmer, you familiarize yourself with the project. You might just know about things that are just not doing well or that are done inefficiently. You might think of something either through reading articles or watching talks, or just by talking to someone. The next one is reports. You might get various performance issues reports from QA, other developers, and playtesters. And the last source is profiling, which is manual, takes the most amount of effort. Right, so here's the thing. Random ideas are not something you can rely on. They might not come up. Reports of performance issues only happen if you're trying to solve a current performance issue. For example, if you are trying to optimize to improve quality, you might never have anyone report a performance issue because you haven't actually brought that out into the game yet. It's also very possible that most players aren't going to recognize performance hitches, but there's still something that we want to resolve. And finally, profiling is scientific. It is hard fought, but if you do it right, and it's the only method that can guarantee results. Now, of course, all 3 origins of optimizations are things we want to use, but the third is the one that we can control, so that's the one we're going to be talking about today. Right, so let's talk about our strategies. Like I mentioned, optimization is scientific. There's a clear goal, and there are defined and provable results. The only thing that we can't guarantee is how much we are going to be able to optimize per pass. So this naturally leans towards a sort of iterative workflow, one where you analyze, optimize, profile, confirm, and repeat. Right, so for us, we settled on a monthly profiling suite. Now, what is this about? The monthly profiling suite is a set of profiling tests that we do where our goals are to find new optimization ideas and also verify that we are going in the right direction. This means that we want to make sure that we catch any regressions in performance. As I mentioned, the game was in active development throughout the time that we were porting the game. So it was important to catch any potential changes to levels, etc., that might have caused performance to degrade. And the monthly profiling suite, as I mentioned, is not a static thing. It is something that we adjusted based on the current phase of the project. It doesn't make sense to do a broad sweep across the entire game if you know that even your simplest base case isn't performing well. Basically, don't waste time. Right, so what's our profiling suite like? It is divided into 4 steps with the goal of narrowing down to a single or a couple different performance issues. Now, we start at the largest overarching level, and we work our way downwards, from the game to individual levels to individual points of interest, to finally a render pass or multiple render passes that need investigation. At the first scope, we're looking at the game, and we're just looking to make sure that we can consistently hit 60 FPS across the entire game. In theory, this would mean that you would have to profile every level, every potential area in the game, which brings up a bit of a problem. King of Meat's a dungeon delver with UGC, which means there's infinite levels. Yeah, we're not going to profile all of them, so fine, we won't test all the levels. We're only going to test the ones that are paired with the game release, and then we're going to hope that the player levels are going to be all right, or worst case, the players will just have to adjust their own levels. Now, that's still a ton of levels, so we work together with our QA to collect simple averages, since they are often running through the game anyway, and they're able to provide us data from a very simple tool that we implemented, which just starts at the start of the level and captures simple averages, max frame times, etc., and can give us basic information about a level. Now, then we have them list all of those stats in an Excel sheet, and this usually gives us some levels that are performing particularly poorly. Either they have a high average frame rate, or they have a high number of frames that are exceeding the target, which usually will show up in like a percentage over there. Right. So using that Excel sheet, we're able to identify a couple levels that we think are doing particularly poorly and we want to look into. So looking at each level here, we want to look deeper. For this, we created something that we call the playthrough profiler. This tool is similarly started at the start of the level and disabled at the end, and collects much more detailed information using GPU timestamps. This can give us basic information like the full GPU frame time across the board, but it can also give us a more detailed frame breakdown for each individual frame across the entire level. Now, of course, this is a lot of data, so we export this into TSV, and then we import it into Excel, where we can process it with various graphs and algorithms. One of those algorithms is displayed here. It is a simple tool that determines the worst performing frames, lists them out for us, and then we can very quickly identify which ones we might be actually interested in looking into. Now, these numbers are a bit old, so we're looking at 30 milliseconds here, but like I mentioned, we're targeting 60 FPS. Right. So when you have a number of horribly performing frames, we basically have what we call points of interest. These are frames that we are going to be looking into deeper. Now, it is possible at this point that we might have too many. A very common situation for us in the start was that the game was just performing like shit, and we needed a lot more work to get it to do well. So often we would have to find a way to narrow this down a bit. To do so, we first matched all of this data with a video of the gameplay, and this helped us simply cut out any points of interest that weren't particularly interesting. Like there's cases where there's a lot of captures of a similar issue in multiple frames. There are often issues that we are already aware of, and there's also stuff that just isn't for us. Like, for example, you might have a heavy frame spike that just turns out to be an explosion in your face that the VFX team needs to look into. Right. The goal here is eventually to select points in the playthrough that have performance issues that we are not aware of, or that we think we have the potential for improving. Right. So the next step is investigation. This is where we look into each individual point of interest. They all likely have some kind of render pass or potentially multiple render passes that are performing poorly. Usually one stands out. If there's multiple, they might have a similar or shared cause. Now, how do you approach finding out what to optimize? That is what we're going to be talking about next. Right, so we're going to be investigating a performance issue and looking for a way to optimize it. How do you do that? How do you optimize something? Well, it really depends on what you're optimizing. We usually take a different approach for rasterized meshes versus full-screen shaders versus compute shaders. Let's talk about the rasterized meshes first, because they are the most interesting to talk about here. Right, so the GPU and, in turn, the rasterization pipeline deals with large quantities of work. Each individual draw call spawns potentially thousands of vertex shaders, which then potentially spawns even more pixel shaders, which then individually have to iterate numbers of lights, etc. So it's incredibly important to catch performance issues at the start of this pipeline and take a top-down approach rather than trying to optimize the individual workload. We're looking to prevent the workload from happening. Right, so what can you reduce? In simple terms, you can reduce draw calls by frustum calling to determine if a mesh is in view, by occlusion calling to determine if a mesh is visible, and you can perform things like distance calling for small meshes to prevent smaller meshes that aren't really going to contribute to the very much from being rendered as well. Next, you can reduce the number of vertices, which is often a combination of effort between the engine and the art team, where you might be optimizing assets, you might create LODs, which you then have to implement. You can, from your end, you can do more complicated things like mesh clusters or triangle calling. But in our use case and in a lot of use cases, I find that the last two are only really worth it if your goal is high vertex density. When you're targeting a lot of lower-end platforms, like mobile phones, for example, or mobile devices, you often can't really push your vert count that high. So the only real way of optimizing here is just lowering your assets. And right. Then next up, we can reduce the number of pixels. Now, a very common approach for this is to use upscaling like DLSS or FSR to reduce the render resolution. That obviously comes at a quality cost, which you might not be willing to make. But on other GPUs, you can also do something called VRS, or variable rate shading, which lets you reduce the resolution that you're rendering at with lower quality trade-offs if you do it well. Then next, inside the pixel shader, we often spawn more work with dynamic sort of like loops that go over a variety of lights, decals, etc. Now, in our case, in King of Meat, we use something called clustered rendering, which I'm sure plenty of you are familiar with. For us, this means we render the lights in tiles on the screen, and we clamp them by the tile Z range, which is enough for our case. As some games with like longer sidelines end up using more complicated binning and the like. Right. Now, before we move on, I want to stress that you don't have to do all of these steps, and you don't have to start top-down, but usually it is the right approach. There are times where you are aware of issues that are in the lower end that are much easier to address than something in the higher part of the pipeline, and it's just easier to do that. But you should be aware that usually you want to start with preventing workload rather than optimizing the workload itself. Right. So learn from my mistake. So in this example, we found out that the main render pass was slow and needed work. So we do a forward plus pass, so we have a death pass and then a lighting pass. And in that lighting pass, we saw that we were performing particularly poorly, and we wanted to see why. Right, so this pass performs a lot of lighting calculations, and it should be pretty heavily pixel shader bottlenecked. But in reality, what we found out is actually that the pixel shader occupancy was relatively low, ranging up to around 70%. Now, in this case, our registers weren't really pushed to the max, so that wasn't really the problem. So we figured, all right, well, it must be something earlier in the pipeline. So we took a look at the vertex shader, found out that it was also not doing that much work, which is weird because you'd imagine that if the vertex shader is fine, then the pixel shader should have plenty of data to work with. Now, in this case, we found out that actually the problem was the step where data had to be passed or load it in from memory into the vertex shader, basically what's called the vertex attribute fetch. And since we were working with mobile devices, that the amount of memory that had to be processed was incredibly high, and it was struggling to keep up. Now, what we try to do is we try to optimize this. Right, so we figured, all right, we are familiar with shader optimizations. We can do this pretty well. So let's try to optimize this from what we can do. So our first step was to try and reduce the number of attributes that needed to be read. Now we have one large Uber shader, but it does have a lot of variants, and those variants often don't need all of the vertex data that is passed through to the pixel shader. So we can often try to avoid, loading in a lot of memory. That didn't really do much. So then we were like, all right, well, maybe we also need to prevent that memory from being contiguous. So we decided to separate the vertex attribute streams in the hope that maybe if we're not using the data and it's not near our current data, then we should have a better time reading other data. Also didn't really do much. So then we tried some more experimental stuff. We tried compressing the vertex attributes. For example, we first tried to just simply combine some vertex attributes where possible into smaller float 4s. Since the hardware we were working with loaded data on a per float 4 basis per attribute. But that didn't really do much either. Then we tried to compress actually compress the attributes by using octahedral packing, where we converted the normals and tangents into a single uint each. Unfortunately, that also didn't really do it for us. So nothing really worked, and that was kind of frustrating because we spent months on trying to make something work, and it did nothing. Right, so let's take a step back. Our goal was to unlock the pixel shader's potential. Now, we were a bit overzealous and immediately dove into vertex shader optimizations, whereas our first step should actually have been to take a step back and look at the actual data that was being processed here. And in this case, what was simply going on was that, at least for this hardware, the ratio of vertex data to actual pixel work was simply off balance. And the only real way to optimize this and actually improve our performance here was to reduce the density of pixels in the frame, density of vertices in the frame. And once we did that, once we adjusted our LODs, once we adjusted the meshes, the art, etc., we easily got to the performance improvement that we needed, which made way more improvements in a couple weeks than we were able to do in months. Right. So now that I've discouraged you from optimizing shaders, let's optimize shaders. Usually, you're going to want to do this after you've looked at all the other steps, but like I mentioned, take that with a grain of salt. If you know something is easy to optimize in a shader, you should do it. If it doesn't take much work and you're almost certain that you're going to be able to improve it much more easily, then you should do it. But yeah, we get to optimizations in shaders. This is also where we're going to briefly talk about full screen shaders and compute shaders, which do not really follow the same rasterized pipeline. So there's not as many steps that we can take that we can reduce in. Now, what we can do is, for things like full screen shaders, we can consider reducing the resolution, which is often pretty applicable for things like SSAO, SSR, and other full screen effects that do not contribute to the final pixels as much as other passes. So consider reducing those passes instead of using upscaling to reduce your main pass further, because that will have much more effect on the game. Right. So shade optimizations aren't really in the scope of this talk. I could go on for hours about investigating deeply into various tooling or using various tools to investigate your shaders and finding ways to optimize them using infinite techniques, but we really don't have time for that. So I'll just give you some quick thoughts. I think you should apply the same concept as the rest of the talk. Waste less, do less work. Now, shaders process a lot of information just like the rest of the pipeline. Your first step should be to reduce. Don't compute any work that you don't have to multiple times. For example, if you can do work on the CPU and then upload it to the GPU and let the GPU take in that data once, that is better than having to do it for each vertex or pixel shader application. If you're able to compute data in the vertex shader, you should do so. If you're able to compute data outside of the loops for lights, you should do so. Next, you should try to reuse data where possible, because you've already calculated it and it's free. So that can be things like using your early depth buffer to occlude lights, objects, etc. Occlusion calling was sort of what I mentioned already, but wherever possible, you should try to reduce your data. And finally, you should try to not recycle your data, because that doesn't make sense. Right, moving on. Right. Finally, in finding optimizations, I think you should consider this. You should know your project. That is really what matters most here. You are the only one who knows your projects, and knows your goals. Optimizations are almost always sacrifice. You are trading off something against something else. And you have to consider, whenever you're thinking about optimizations, what you're willing to give up. Now, usually, the less you're willing to sacrifice, the longer it is going to take to make that optimization still work. It's a lot easier to just say, OK, we're going to do a less complicated level than it is to say, OK, we are going to try to make this beautiful open world game. Right? But if you want a beautiful open world game, expect to spend potentially years optimizing it. So yeah, it depends. The sacrifice is either one of time or quality, depending on what you're willing to give up. Right. That also brings me to my next point. Optimizations are sacrifice, and you shouldn't add them blindly. They introduce complexity into your code base. They potentially introduce a loss of quality, and it's also possible to make mistakes along the way. So you should make sure that your optimization actually does something. For us, that means we profile our game before and after the optimizations to make sure that there's actual provable impact. And then we also provide screenshots and videos from the game before and the game after to make sure that we are catching any potential regressions and that we are OK with the quality loss that might have been imposed. Right. So let's talk about how this all fits into the usual structure of game dev. Oh, wrong button. Right. So luckily, the approach we take with the monthly profiling suite is pretty agile, and it can easily slot into Scrum or anything alike. From our end, we got a lot of trust from our producer, which meant that we were able to sort of invoke our own planning structure around this profiling class and make it all work. But if you have less power, you might have to work more closely with whoever's in charge. The profiling suite doesn't just provide us with new ideas and new tasks. It also provides a status update of our work. We're able to reevaluate our direction every month based on the profiling suite, and we plan our workload in sprint-like manners on a bi-weekly basis. Right. So how do you actually prioritize what work is most important? This is somewhat subjective, but you can determine some loose metrics. We usually discuss and rate the potential performance improvements based on the impact on the game, the impact on performance, the complexity that comes with implementing it, the risks, like what kind of things could go wrong trying to implement this new feature, what kind of bugs are we introducing that we're going to have to deal with later, and the visual sacrifice that we are making by implementing this technology. Now, the way I always go about this is every idea that you have should be considered and should be written down. Even if you think that a performance optimization is not worth its sacrifice at this time, it might be something that may come into use or reconsideration later, especially if you're pushing deadlines. Right, that brings me to my next point, which is how do you stay on track on a longer-term basis? The first point here is that optimization work isn't always guaranteed. You might spend months optimizing something that doesn't work out, like us. And then you need to still make up for that time. So leave leeway in your planning, which is easier said than done. You don't always have time for leeway, I know. Now, first, what you want to do is you want to determine your goal, right? You have a certain frame rate that you're currently at, and you want to reach a certain target. And you need to figure out when you need to reach that target as well. Then we simply divide that time span into reasonable chunks that we're sort of intermediate targets that we're hoping to achieve along the way. And yeah. So to give a bit of an example, this is sort of at an earlier phase of a project. We were looking at 30 milliseconds. We were looking at a 30 milliseconds target over the course of 4 months, and our current frame time was 45. So in that case, we set up a 5 millisecond per month goal, and left around 1 month of leeway to catch up. Every month we profiled and analyzed as we discussed, and we tried to implement techniques that we thought were actually going to be helpful, but we also left some of the worst sacrifices to be able to catch up should we fall behind. In our case, that wasn't needed because we were able to estimate our performance improvements for individual tasks quite well, but we did have fallback tasks in case things went bad. Cool. All right, so let's quickly go through the takeaways. I believe I'm running out of time, but I'll try my best. All right, so optimization is scientific. There's a method to the madness, and if you're doing it for long periods of time, you should have a structure. The approach we used allowed us to make decisions backed by hard data, which we were able to reference along the way. The monthly results provided a record of our work, proving that we were following a good trend and catching regressions along the way. I would like to press that don't let it get stale. Our workload evolved over time because the project evolved over time. There were different phases, different points of the optimization, and you should try to adjust as needed, just like you should with Scrum. And finally, it worked. This approach worked for us. We had measurable results. We had a backlog full of potential work. Our most valuable work was prioritized. We hit our performance targets, and we had consistent and significant performance improvements along the way. That was my talk. Thank you all for listening. I don't think we have time for questions. To quickly round it up, there are wrong button again. There are some sources here that you can reference. We are also hiring a senior and principal programmer, and you can connect with me on LinkedIn using this QR code. Thank you.
Thank you so much, Leon. So unfortunately, we're out of time.
Yeah.
But you'll be around, right? So
absolutely.
Anyone can just come up and ask any questions afterwards and during the breaks. So thank you so much.